is on millimeter wave and terahertz communications, and the chairperson will be Umberto Spagnolini. Umberto, please.
Thank you, Antonio. So a lot of interest about millimeter wave and terahertz. I'm waiting a little bit in the meantime that people are entering. So a lot of interest about where to find the spectrum. Millimeter wave and terahertz is expected to be the way of where to go. So the first presentation will be given by Antonio D'Alessandro, which is from La Sapienza in Rome. So, Antonio.
Thank you very much, Umberto. Waiting for the slides, I'd like to thank the technical scientific committee of the project for giving me the opportunity to present our contribution in Sapienza to develop a terahertz receiver for future mobile technologies and 6G, and these activities are within the spoke tree of particular structural product dreams and the FOX project T-Next. This is an outline of my talk. I will start from the core of this receiver, which is based on a MOSFET, and in particular by using a nonlinear effect, the so-called self-mixing effect, which I will mention briefly. And then I will show the simulation in TCAD, where we implemented the equation to study the effect and in particular the terahertz response. Then we will go through the design of the entire receiver by using the 55 nanometer BCMOS technology developed by ST Microelectronics. It's really a very nice opportunity for us that thanks to Restart, we had the opportunity to collaborate with ST to implement our project by using their BCMOS 55X technology based on a 55 nanometer. Actually, it's a 60 nanometer shrink technology developed by ST, and then I will go through the main features of the design of the terahertz antenna, the circuit modeling, and the optimization in terms of signal-to-noise ratio in particular, and bandwidth. Then we will show the main features of the chip layout. We just completed going through the very rapidly through the electrical schematics with the 4 antennas, the common mode feedback amplifiers, and then the circuit simulation. Then just from brief conclusions, which are not the conclusion of the work because it's still in progress, but which will conclude my talk. So we will start from a simple MOSFET in which we can observe in a so-called self-mixing effect, which is a nonlinear effect for which a rectified DC potential, the drain, can be obtained proportional to the square value of the terahertz potential applied to the biased gate source port. And here the nonlinear equation, which I will not show you because a reason of time, also not to bore you with the equations, but we implemented the equations to study the self-mixing nonlinear effect. Here you can see the distribution of the potential between gate and source for a 100 millivolt between gate and source. And I would like to drive immediately the attention to the fact that this is important, the bias of the gate and the source. And we have a maximum field at the source oxide gate corner where the potential gradient there goes to the steepest variation. Here is the simulation which show you which shows the potential at the drain, and for various for different values of gate source voltages. As you can see, we had to optimize the gate source voltage because above a certain value, the potential of the drain decreases. So we need to optimize the maximize the effect at the drain. And so this is a sketch of the rectifier followed by a low noise amplifier, in which the width of the rectified transistor and the width of the low noise amplifier are crucial geometrical features to be optimized during the design, along with the gate source voltage, as I said, and then the voltage at the source of the low voltage amplifier. This is just a schematic of a picture of the antenna that has been designed by considering the metallization planes available in the technology provided by ST. And here on your right-hand side, you can see the optimization of the resonant frequency, in which the arrow just shows you that there is it is required to have an inductance component in the design of the antenna, because we need to compensate for the capacitance effect in the detector, so we can have the optimal antenna plus detector operation. As you can see on the left, the study of the series resistance and the reactance of the detector versus the gate voltage. These were made at 0.7 terahertz frequency, and this is the equivalent circuits to study the signal to noise ratio. In particular, on the left-hand side, you see the self-mixing produces a rectified voltage, so we take into account the noise component. Also on the right-hand side, for the low noise amplifier. Okay, so here is the just to see the simulation implemented in TCAD of the rectifier, in particular the output voltage and the output resistance for different values of the source voltage of the rectifier. And again here, the transconductance of the low noise amplifier. In particular, I like to draw the attention on the output noise, where we have a noise corner frequency of 45 megahertz, which is important to be given as input for the amplifier chain, amplification chain which follows the low noise amplifier. Okay, and then further optimization. I just show you this picture, but this is not. This is a result of a Monte Carlo simulation, which put together all the parameters in order to calculate the minimum power density at the plane wave impinging on the structure versus frequency for different values of the width of the low noise amplifier. And here this is the schematic, the overview of the chip layout developed by using the BCMOS 55X technology, including two antennas operating at 0.6 terahertz and two antennas 0.7 terahertz, considering that this technology can be scaled. Of course, this is just a details of the two antennas and the amplifiers. I'll go very quickly here, just to give you the full receiver electrical circuit schematic, and I'd like to draw the attention on the amplification stage, which is provided with a common mode feedback for offset compensation output stage at 50 ohm, and just the details to give you an idea of the circuit. But then the circuit was at the end was simulated showing a bandwidth between 30 and 150 megahertz, where the signal to noise ratio is higher, with the maximum gain over 40 dB. Still, we have a good gain at 24 dB at 1 gigahertz. Sorry. Okay, and that I like to also show how we spend the money of the project in preparing the setup. For testing the chip, which has been sent to the foundry, so they are now doing all the checkings. In the meantime, we are developing the transmitter change for the test chip testing by using these multipliers that were Virginia diodes, analog devices that were purchased with our funding. And then in conclusion, just we finished the design of the chip layout by using a self-mixing effect in MOSFET to develop the terahertz receiver, which is a scalable technology, thanks to the collaboration to ST Microelectronics. And so we are continuing to work on designing the PCB and the packaging of the chip in the meantime. And I'd like to acknowledge all the team in Sapienza who collaborated to develop this contribution. In particular, also Carlo Santini is our RTDA researcher paid by Restart, so we are pretty happy about that. And we hope he can continue. He's a good guy. And also I'd like to acknowledge the collaboration with ST Microelectronics from Crolles, close to Grenoble in France, in particular Pascal Sevaleri and Frédéric Monsieur. And I just this concludes my talk, and thank you very much for your attention.
Thank you. It's time for comments, questions, or curiosity.
Thank you for a nice presentation. Just a curiosity. So if you want to establish, let's say, long-range terahertz communication, there is no way we need to use a massive MIMO technology. So that I mean hundreds or thousands of antennas. So the question is how all this can be is scalable if you want to realize in terms of energy consumption, in terms of I don't know, other aspects that.
Yeah. I mean, this is an intermediate stage, as you can imagine, where we want to test our design to prove the design. But we follow this approach because it is scalable. So we will proceed. I mean, as our representative from the ministry said that we can continue, we hope to continue further to develop with this project if we will have a good testing after receiving the chip.
Antonio, I have an easy question. People typically expect terahertz, a large bandwidth, and you show something like 150 megahertz, which is not a large bandwidth. So can you say something about that?
No, well, actually, we are using silicon, so there is a limitation on that. But the idea is to use the terahertz as a carrier. So, and then we have bandwidth for a baseband signal. So this is the idea. Otherwise, we need to do with another technology.
Okay. Okay, thank you again. So the next speaker now is Antonio Malacarne, which is from CNR and PN Lab in Pisa. Floor is yours.
Hello, everybody. Good afternoon. So, I'm gonna show you now some recent results on the realization of a low phase noise optical local oscillator for millimeter wave radio transmission. Okay, so this is, first of all, let's start from the background. So I think most of you already know why this millimeter wave band generation is becoming important, and it's already planned to be used in forthcoming 6G standards. It's already deeply employed in automotive radar, so for both communication and sensing. And in W band, for instance, which is the band where we focus with this work, there are already some lightly licensed sub-ranges for wireless and satellite communications. And this is also a frequency of interest for this hot topic, recent hot topic of joint communication and sensing. And in all these applications, of course, the stability of the generated tone, so the RF tone, and its phase noise performance are crucial for both communication performance and sensing performance. So, so now in this work we focus on telecom, so in particular on OFDM transmission, or in any case a single carrier data transmission. For OFDM in particular, this type of signal is susceptible to phase noise. It induces both common phase error and intercarrier interference. And of course, the impact is higher and higher if you go with the higher modulation orders, with the decreased subcarrier spacing and higher carrier frequency, the generated carrier frequency. So there are DSP techniques quite efficient against the CPE, but not so much against ICI. So we should try to limit ICI and therefore to achieve a very good phase noise performance. And this is our main goal, one of our main goals actually. Some more motivations for us. So the use of photonics for generating millimeter wave band. So why? Because it guarantees wideband and also reconfigurability, so flexibility in generating different frequencies. And also, since our approach in the end generates a signal in the optical domain that then after photodetection achieve the upconversion to millimeter wave, this means that you can transmit the data signal before photodetection through low-loss optical fiber. And also we go in the direction of photonic integration to miniaturize the solution, because the solution can be more stable, and of course in light of reducing possibly fabrication costs. And then we also focused on the realization of advanced optoelectronic packaging for the device. So millimeter wave generation can be realized with pure electronics solution, but typically with the solution, of course, phase noise increases when you increase the generated frequency. There are a number of solutions in literature exploiting photonics approaches, including heterodyning of optical frequency combs. You can achieve very nice phase performance at quite high frequencies approaching the sub-terahertz, but in our opinion, this solution is still not so mature and not so stable. So we recently proposed mainly two approaches. One that is a photonics-based way to frequency multiply the lower frequency of a local oscillator, and another solution where we basically phase lock two independent narrow line width lasers together. So you can see there pros and cons of each solution. In the first case, if you start with a local oscillator with a very good phase noise, you can achieve good phase noise performance, but of course phase noise scales with the square of the frequency, so with the square of the multiplication factor in this case. The solution can be monolithically integrated, as we did actually, except for the laser source. And currently the solution we packaged, as I will show briefly, presents high conversion losses. In the second case, the nice thing of this solution is that the phase noise that you achieve is partly, the phase noise performance is partly independent on the generated frequency. And you can achieve a higher optical power at the output of the scheme, so therefore also a higher RF signal in the end. But this solution requires very narrow line with lasers, as we will see. So this is a sum up of recent results we achieved in generating 100 gigahertz tone starting from a local oscillator at 20 gigahertz. So here you can see, I don't know if we have a pointer. Okay, anyway, you can see the scheme on the top on the left. So we have an external laser entering the peak. The peak divides the laser into arms. In one arm, we generate an optical frequency combo through phase modulation driven by the lower frequency local oscillator. Then we select with an integrated optical bandpass filter one of the harmonics, and we couple it back with the laser modes. And then you can place the photodiode even remotely. So you can go through optical fiber, and then after photodetector, you get the millimeter wave generation. That basically has a frequency that is a multiple of the local oscillator frequency. So we realized our mask layout, the chip, we tested the chip, and then you can see in the end the phase noise performance. So the blue curve that is comparable with the violet. The violet is an ideal frequency multiplication of the local oscillator, that is the yellow performance. So we have some excess noise in the low offsets due to the accuracy of the thermal stabilization of the peak, and in the high offset regime due mainly to decrease of SNR. So because of optical losses introduced by the peak. So the core of the peak is this optical bandpass filter that has been realized through a distributed feedback resonator. So we basically cascade the Fabry-Perot cavities. In each cavity, the mirrors are realized through Bragg gratings, which are sidewell corrugated silicon waveguide sections. In between each pair of mirrors, we placed a phase shift section thermally tunable. And then, so properly tuning these microheaters, we can shape and we can tailor the bandpass response in between a wide stop band region, that is the mirror response, basically. And we have, in particular, two ways to tune the filters, through the microheaters or through a long top metal heater all along the whole structure that rigidly tunes the whole spectral response passband plus stop band region. So, yeah, okay, I forgot to say, we achieved a bandpass bandwidth from 1 gigahertz up to 10 gigahertz with a passband loss of 1 to 2 dB and a nice rejection. I mean, the shape is very steep, so, yeah. Okay, so, yeah, we made the optoelectronic assembly of this peak. So we designed our own PCB with a custom bias T for supporting high RF power, because to generate the combo we actually need a power comparable to 1 watt, even a little bit more. And we also analyzed what happens in case of a different length of the wear bonds and different load impedance on the PN junction to realize the phase modulator. So to check the impact on the S parameters of the PCB. So in the end, we used that source for a millimeter wave radio transmission experiment. This is indoor, so with 2 antennas, just one face to the other at 2 meters distance. We generated QPSK and 16QM signals up to 4 gigabit per second, mainly because we were limited to the operation bandwidth between 92 and 94 gigahertz, and this is due to the employed W-band devices. We are currently extending to 92, 96, that is actually the down converter range. By changing the filter, the amplifier, the filter and the amplifier. So here you can see the error vector magnitude measurements on the right, and the reconstructed constellation for 4 gigabit per second QPSK. So you can see there the legends, the cases where DFBR is written indicates the use of the integrated filter on the chip. The cases where WS is written indicates the use of an external wave shaper filter for selecting the harmonics of the comb. So you can see comparable results up to very high out. So the x-axis reports the optical power reaching the photodiode. So when we reach high optical power at a certain point, performance with integrated filters saturates, and this is, again, due to the optical losses that we surely have to improve. So this is the main reason why we compare with an external filter. Okay, so the second approach, so 2 lasers, narrow linewidth lasers, locked together. In this case, we made use of devices provided by OE Waves, both the laser phase locking system, which reaches up to 40 gigahertz currently, and the 2 narrow linewidth lasers, which exhibits a very, very narrow linewidth down to 60 hertz, more or less. So since this approach and this scheme in the end is limited to 40 gigahertz, we anyway had to somehow multiply the obtained frequency to reach our W-band regime. So in particular, we realized here 88 gigahertz, and then with a 5 gigahertz intermediate frequency, we meshed the down converter frequency range. So here, the phase noise results. Of course, if you compare the yellow and the violet curves, the reason why the violet behaves better in the high offset frequency regime is because the multiplication factor is lower. It's ×3 instead of ×4. Since you start from a phase noise that in that regime is basically the same, you get a better result. Then, here once again, we used that solution for our transmission. Here you can see the results. And in this plot, we compared the frequency multiplication in the dashed black with the 2 phase locked lasers solution in blue. And you can see that performance are a little bit worse when you go up with the baud rate of the QPSK, so for 4 gigabit per second. And the reason is that phase noise is actually worse. For the rest of baud rates, the performance is the same actually because we are limited by the noise floor introduced by the down converter, so that's the only reason. But, okay, what I want to say here is that in principle, if you can achieve this solution with you can achieve the frequency of interest, so you can make the phase locking system working up to the W band. In principle, you can even outperform the other solution because this solution provides benefits. The higher is the frequency that we can generate because part of the phase noise that we achieve is independent on the frequency. Very last device, we recently realized this filter that is basically a multi-resonance frequency. So by using that filter for isolating the comb lines, do not provide flexibility anymore. So we design a filter for a specific frequency to be generated, but this scheme has very lower optical losses. Indeed, if you see the phase noise performance in the end there, our phase noise performance now is identical to ideal frequency multiplication. So we are planning to package this solution and employ this solution for the final tests. So, okay, here very recent OFDM transmission because we are working also on the DSP part of the receiver. So we were able recently to achieve the numbers that you see there. So 4.5 gigabit OFDM with 1.2 gigahertz bandwidth and 6 with 1.6 gigahertz bandwidth. And with the subcarrier spacing that matches the current 5G standards. Okay, it's the second movie. Yeah, we can skip it. So that's it. This concludes my talk. So the results that you saw here belongs to the experimental activities in two structural projects in Restart. One is Rigoletto, the other is Pesco. And all these works are made in collaboration with the Sant'Anna and Ericsson Research Lab, both in Pisa, and you can see there all the people involved in all these activities. Thank you for the attention.
Perfect. One quick question.
Thank you. Thank you, very amazing results. I have one question about the first approach, clarification more. Do you need a closed loop control of temperature of the heaters, or you just apply power?
On the heater, we just apply power. We need accurate temperature stabilization of the whole peak, but we just use a big Peltier cell for the whole peak.
Okay, so the heater, there's no closed loop control?
No.
Not necessary?
No, because,
It's
I mean,
stable enough.
there is these little temperature fluctuations that lead to phase noise because it's the filter that is, if possibly we can even make this more stable, we are open to
So
upgrades.
perfect. We are just in time. Thank you again.
Thank you.
Thank you, Antonio. So next speaker is Stefano Buzzi, which is, he has a dual affiliation. He's University of Cassino and Politecnico Milano. Is on Politecnico Milano for this specific activity. So, Stefano, to you.
Okay, thank you, Umberto, for the introduction, and thank you, everyone, for staying here, and thanks, of course, for the invitation. Okay, I have to apologize because, it's not, it was not decided by me, but my presentation is not about terahertz or millimeter waves, but actually is more on wireless communications, in particular non-terrestrial networks. And this is a presentation of a work that has been carried in cooperation with the University of Cassino and Politecnico di Milano and the University of Parma. And what is the motivation of this work? Okay, the motivation of this work is that for 6G, there is wide interest about cell-free massive MIMO network deployment, where we use, instead of using a large base station equipped with large antenna arrays, we use a sort of distributed MIMO, so several access points that are deployed over the area of interest, and the access points cooperate in order to serve the users. Okay, you see here, for instance, that every user can be associated to a certain number of access points, and vice versa. Every access point can serve a variable number of users. And this structure is of interest for 6G because for several reasons. Here I have just highlighted some of them, in particular that are relevant also for satellites. We can have macro diversity gains because we have several paths between the network and the user, not just one in the case where we have just one base station. And this can be energy efficient, and also we have generally good channel conditions because since there are several access points, the user has the chance to choose among several access points which are the best. So generally, we have much better channel condition than in case where a standard multi-cell deployment is used. So we wanted to see if these advantages or some of these can be extended to the satellite case. Okay, so we focus on a scenario where there are multiple satellites. In particular, we think of a LEO constellation with a large number of small-sized satellites. Starlink could be a good example for what we are considering here. And so we have multiple satellites that play the role of access points. We have multiple users, and we want to investigate the case where multiple satellites a given user on the ground can be served by multiple satellites by taking into account the presence of Doppler shifts. And also in cell-free, one of the problems that we have is that of phase alignment, because since cell-free is based on joint coherent transmission, we want to have that the access points that transmit to the same user transmit the signals with the phase such that the contributions from the several access points to the user combine coherently at the, with constructive within a constructive way at the user. Okay, this is very complicated, actually very difficult to realize. So in this work we look at this hypothesis. So we say what happens when there is not such a perfect alignment. So we have some initial results on this. And in order to do this, we consider, first of all, a channel model where we assume that there can be just one path. So there is a line of sight between the satellite and the user on the ground, but this link can be shadowed. Indeed, the raw PQ, that is just the gain between satellite P and user Q, can be, it's a shadowed variable, okay? So it can be also with an amplitude that is much smaller than 1, very, very small. So we can take into account also shadowing effects. And we do this analysis with, by considering 2 different modulation schemes, in particular OFDM, that is the standard modulation for 5G, as you know, and OTFS, that is a kind of a new modulation that is of interest for satellite communications because it is claimed to be robust, to offer better performance in the presence of Doppler shifts. So we consider these two different modulation, even though this is not really the true focus of our work. Okay, actually we are able, with some details, with some mathematical efforts that are reported in the paper that I'm going to show you in the next slides, we are able to derive for both of these modulation of a unified model that is able to determine the signal that is received on the ground from a given user, highlighting the contribution of the transmitted bits that are in the vector XQ. These are the symbols intended for user Q, and highlighting the contribution from the given satellite, from the other satellites that are transmitting to that same user, and also interference from the other downlink transmission from the other satellite. So we have a very general model that permits to treat in a unified way both OFDM and OTFS. Okay, so we want to study the effect of phase asynchrony. And we do this and assuming system parameters that you see in that table. In particular, we have we are at a carrier frequency of 5 gigahertz. We present here results for the case where there are just 4 users served by, and there is a total of 28 satellites. And there are uniform planar array used by, of course, the satellites and the user on the ground. And we investigate basically 3 situations. The ideal situation where we have perfect coherent joint transmission, so the ideal case where we are able to perfectly align the contributions. Then non-coherent joint transmission where we transmit with a random phase, so we don't care at all of having this, trying to do this phase alignment. And then we have this imperfect coherent joint transmission where we assume that we have done some alignment of the phase, but with some residual errors. Okay, so these are the results that, some of the results that we have obtained. By the way, these results are reported in this contribution that was presented a few months ago in Lucca. And here we see 2 plots. They both show the cumulative distribution function of the SINR, so the signal to interference plus noise ratio per symbol. And for the case where we have a perfect and ideal synchronization of the phase, and for the case where we have a completely asynchronous. The blue line corresponds to the case where there is no diversity. So the blue lines is the same in both situations. But then you take into account what the effect of multiple, when you combine multiple satellites, and you see is the number of satellites that is serving the same users. Okay, from the plot on the right, you see that if we have multiple satellites in general, and we have the ideal assumption of perfect synchronization, the diversity is beneficial, of course. So the performance improves also considerably. But if we are in the case where we don't care about the synchronization, so we don't take into account the synchronization error, and we don't do anything in order to compensate for it, we see actually that there is a crossing between the blue curve that corresponds to the case where there is no, there is just one satellite serving one user, and the other curves that correspond to the case where there are multiple satellites. In particular, we have a crossing because, of course, in the upper part of the CDF, it represents the case where we have a constructive interference of the contribution, but for most of the cases, actually for about 50% of the cases, the interference will be destructive and we have worse performance. In this other plot, instead, we consider the case where we have a partial synchronization. In particular, the blue line is the case now is the case where we don't have any synchronization at all. The rightmost curve is for the case where we have perfect synchronization, and the other curves in between, the other lines in between, are for the case where we have a limited amount of residual alignment error. For instance, beta equal to p over 3 means that the phase error is in between minus beta over 2 and plus beta over 2. So there is the phases are not aligned, but the misalignments has a magnitude that is uniform inside this range between minus beta over 2 and plus beta over 2. And this actually show that we don't, limited synchronization errors can bring, if we are able to align the phases with, even with residual errors, we are able to have a big gain with respect to the blue case where we have completely random phases. Here we have a capacity results. And for capacity, of course, we found that it is always beneficial to have multiple satellites, and that is because, of course, we can always try to find a scheme that is able to exploit the multi-satellite diversity. Okay, this basically concludes what we have done, what we have presented in this paper, this spoke paper. Next, this is something that is not yet has not yet been published. Basically, we want to the idea. I plot just one curve and then stop. What we want to do here is to use the multiple antennas at the user in order to separate the contribution coming from different satellites and then combine. So we want to try to resolve the phase misalignment by trying to isolate the contribution coming from the several satellites at the user and removing the phase uncertainty and then combining them. And actually, we have some results that give some good initial hope for good results. And in particular, what we have done is, one thing that we have seen is that it is important in a satellite environment to ensure that there is a minimum separation between users that are served by the same satellite on the same time frequency slot. Okay, I skip to the final slide. Okay, we are basically investigating this problem of phase misalignment in a multi-satellite system, let's say in the non-terrestrial version of self-free systems. And we have already found some way in order to mitigate this problem. We are doing, now we are currently working on power control as a measure to further possibly improve performance and mitigate this effect, and also to some other solutions that hopefully will be presented in the next plenary meeting. Okay, that is all for now. Thank you very much.
Comments, questions? Nothing. So I have one. I have a couple, but I limit myself to one.
Okay, good. Good for me.
No, my comment is related to the fact that you model the interference coming from the other satellite. But since those other satellites are not coordinated with the network, the set of the satellite that belongs to the same operator, since they are not coordinated.
No, actually they are. In our case, they are, of course, because they are.
So it never happened that you have this interference not to be Gaussian, but perhaps is, I don't know, it has a burst of interference which is non-stationary or something else.
Well, for sure is non-stationary, but this is just like the same way in which we model interference in a terrestrial network. So we assume that in a terrestrial network, we assume that there are several base stations that transmit to users in the same time frequency slot. So a user receives its own useful signal from its own base station, but also receives interference from the other base station, because that are transmission intended for other users, and we do exactly the same. So we assume that there is a large number of satellites, a large number of users on the ground. We make the association between users and satellites, and then every satellite transmits to its own intended user, and we model all the interference. It's in the SNR expression. So but of course, I mean, what we can say is that since at the satellite you don't know the channel, but you just know the position, it's based on analog beamforming. So you just send a beam towards the position where your user is. So you have all the side lobes that produce a lot of interference, and that is a problem.
I can imagine. And the phase only is enough to model this asynchrony?
No, here for the phase we are just modeling the fact that if two satellites serve the same user, the signals transmitted by these two satellites arrive at the user with not aligned in phase. Okay. Then there will be to model also the time asynchrony, but that's another story. That's another story.
Okay, thank you. Thank you again for Stefano. Thank you. So last speaker for this millimeter wave terror session is Vladimir Pusra. Go, say yourself.
Thank you very much.
Okay.
Good afternoon, everyone. I'm very grateful to the organizers for being here. And yes, my name is Vladimir Pushkaryov. I am from the group of terahertz photonics of Professor Miriam Vitiello in CNR Nano. And today my topic will consist of two parts: terahertz wireless communication and terahertz detectors on integrated photonic platforms. At the part of Spoke 3, our team is devoted to the DREAMS and TNEX projects, which deal with the micro and terahertz waves. And regarding the terahertz waves, it can be characterized with respect to telecommunication by the high carrier frequency. Also, it is inherently robust to the against the relay scattering. However, it is also prone to the atmospheric absorptions, and thus this radiation may pose an interest in the short-range terrestrial communication and inter-satellite links. Unfortunately, conventional materials are hardly able to operate in this frequency range, and that is why one of the materials which we are focused on is the graphene. In particular, graphene has brought a real breakthrough in the field of photodetectors due to its high charge carrier mobility, broadband absorption, and ability to operate in wide frequency range. On this note, let me move to the first main part of my talk, which is development of the terahertz free space optical link. Namely, we suggest the system which operates with the 2.86 terahertz efficient quantum cascade laser and room temperature graphene-based FET photodetector. As you can see from the scheme, this system can be divided into the transmitter and receiver block. Each block has the digital sub-blocks for encoding and decoding information, and encoding of the digital information is done through the intensity modulation. Then the signal is converted back to electrical by the graphene photodetector. The digital RX unit counts the correctly received packets, and by this calculating the packet error ratio. So in our system, the QCL, the quantum cascade laser, is hosted in the compact Stirling cryocooler, which support the transportable solutions, and it allows 1 milliwatt optical power. Despite the quite high bandwidth of the transmitter and receiver, in this particular conceptual system, we had a limitation of the overall system bandwidth due to the required high values of the gain of the transimpedance amplifier, and also maximum modulation bandwidth of the current driver. That is why our results today will be presented for the two particular values of the bit rates, 115 kilo and 1 megabits per second. These values corresponds to the two specific value of the amplifier gains. So if we measure if we will record the packet error row as a function, packet error rate as a function of the signal amplitude, we could retrieve the values for the optical power at which the system operates below the error-free thresholds. The 2-eye diagram on the bottom actually corresponds to these high optical power values, so within the error-free threshold, within the error-free range. Taking these values, and then also employing the specific propagation model, we can estimate the error-free communication length or distance for our system, which appears to be 128 and 274 centimeters for 1 mega and 115 kilobit per second respectively. Now, if we would choose favorable the transparency window, for example 3.44 terahertz as suggested by the absorption function, then with the reported QCL laser in this range of 3 milliwatt, we could achieve the using this model, we could predict the distance of 5 and 7 meters respectively. So it is obvious that the graphene-based efficient receivers is a key element not just in our system but in many telecommunication applications, and that is why we are focused on the scalable synthesis method and also possibilities to integrate the single graphene layer into the photonic platforms, which would improve the light guiding and light coupling of the detectors. So this is essentially the second part of my talk, where I will speak about in this regard, about the detectors, namely the antenna-coupled p-n junction graphene photodetectors based on the photothermoelectric effect. This kind of antenna allows us to control specific area of graphene and also effectively tune the properties such as carrier density, chemical potential, and absorption. The concept of the device is the following. We employ, for the photonic platform, we employ the graphene Salisbury screen, in which the CVD-grown graphene layer is positioned usually at the distance of quarter wavelengths from the highly reflective surface. We integrated on this scheme the planar bow tie antenna.
Here you can see the layer by layer this schematic sketch of the device, of the detector. Note that we use the polymer called polyamide for the spacer. And this slide showed actually the microscopic picture of our fabricated antenna. And geometry properties of the device were calculated using electromagnetic simulations. Surprisingly, the optimal thickness was in our case with our materials not quarter wavelengths, but 1/3 of quarter wavelengths of the corresponding terahertz power, which we used 2.86 terahertz. And we first characterized the transport properties of the device by monitoring the resistance of the graphene channel as a function of applied left and right graphene gate voltage. This resistance map which we get allowed us to retrieve some electronic parameters of the graphene and of the device, and actually they correspond to the data or to the results of the other devices on the semiconductor substrate like silicon, which means that our polyamide, the spacer layer, does not affect the properties of the graphene. Next, we perform the optical measurements by focusing our terahertz light onto the detector. We retrieve actually the distribution of intensity distribution in the focal plane by precise controlling motion of raster scanning of our detector, which is quite small, and it results in the very nice diffraction pattern, which corresponds to IRI disk with actually 8 orders of diffraction and signal to noise ratio of 2000. We measure responsivity as a function of the gates voltages, and we got the results actually which are order of magnitude larger than reported results for the other photodetectors using CVD graphene. Using the responsivity map and the resistance map, we retrieved the noise equivalent power as a function again of the gate voltages, and we get the minimum room temperature noise equivalent power below 300 picowatt per square root of the frequency. And lastly, we measured the linear dynamic range of the device, and you can see from the graph that we got 4 orders of magnitude wide power dynamic range, a minimum detectable power level below 10 nanowatts, and also we measure response time, which was about 5 nanoseconds. So from this, I would move fast to the summary. I present today the results on 2 projects. One is a free space optical terahertz communication. We showed that we can suggest some transportable cryogenic liquid-free setup, which based on the prediction and existing tools can ensure the from 5 to 7 meters distance error-free communication, and also show the design and fabrication of the photodetector on the optical integrated onto the photonic platforms, which have a very nice figures of merit. And this work was, of course, the result of collaboration of many people. And I don't have much time now to note everyone, and I at least want to thank the leader of our group, Professor Miriam Vitiello, then the leading scientist, Leonardo Vitti, who contributed mostly in this project, and also all of you for your attention. Yeah.
Thank you, Vladimir. So, questions, comments? No, I do myself. So in the last number you showed, anyway, I remember that. So the last number you showed was that the time response was 5 nanoseconds, right? Yeah. So this number maps to our community in terms of bandwidth. Because, if you have a response of 5 nanoseconds, the inverse of 5 nanoseconds, more or less, is giving you the feeling of, how reactive is the circuits, right? Yeah. So, if I'm not wrong, makes, I don't know how much it's doing, So, it should be 500 megas. So, so you have a capability with your system to have a bandwidth that is 500 megahertz. So how can you improve that? Use the microphone.
Yeah. So the response time is not the strongest option, but we should work on it. I'm not sure that now I have the solution for to this one, because the design of this antenna actually is. I don't have time to explain everything why this specific design is important, and this configuration of the source and drain contacts, because usually the response time can sometimes be improved by proper adjustment of the geometry of the device. In this ways, we will see if we will be flexible enough to change it.
Okay, thank you for for everything. So thank you again, Vladimir. So thank you all for attending this session on millimeter wave and terahertz, and the session is closed. Thank you all.
The last session is on verticals and will be chaired by Maria Elisa Melani. Maria Elisa, thanks. You can go there. Thank you, Maria Elisa, for chairing the session.
Okay, so good afternoon, everybody, and to all the bravest among you who survived until this very last session of the very last day of the workshop. So we are going to have 4 presentations here, and since ladies come first, we'll have a slight modification to the order. So first, I'm sorry, Antonella Poce from the University of Tor Vergata will deliver her speech. So please, Antonella. 5 minutes sharp, I'd say, maybe a little bit less more. A little bit
Go
less.
as fast as I can. Thank you so much for having this opportunity to present our part of research carried out in Roma Tor Vergata. I don't know if the presentation, yes, I remember I have to. So our work is set in the area where sorry, this is not the one I sent this morning, but anyway, we'll go on anyway. The work we have been carrying out is set in the Net for Future area. It is connected to the possibility to harmonize the results of Restart into some emerging social goals. So the promotion of social and cultural inclusion, the development of well-being for users and target community, and the development of soft skills, active citizenship, and cultural expression. There are connections as far as vision, synergies between projects, user perspective, and shared tools are concerned. We will use, and we developed, we had the possibility to have some tools to communicate certain contents. We installed some totems within the university area, the engineering university area. We will use, and actually we are using these totems to communicate certain contents, but especially within the totems we developed some extra tools, especially a virtual museum that has been created, and a LED wall that will broadcast contents that are available at the totem, where interactive activities will be carried out to the wall of one of the buildings at the university. So which are the goals? Enhancement of cultural heritage of the area, so communicating cultural heritage, sustainability and innovation, welfare and social inclusion, collaboration and connection, and dissemination of results. which are the possibilities that we reach through the totems that are connected to the 5G antenna that is placed on one of the buildings within the engineering area in the campus in Roma, Tor Vergata. The totems, as you can read here, will be connected via 5G network, ensuring fast transmission and integration with other devices, such as the LED wall. And each totem will serve as a connection point within the public, between the public, local and cultural heritage and the content created, allowing participation in multimedia and interactive experience. What do these totems do? They will stream high-resolution content related to the Restart project contents. They will offer immersive live experiences, allowing users to access real-time content directly from the ground. They will enable advanced digital interaction. Totems will be equipped, actually are equipped to enable users to access educational and information content, participate in augmented reality and virtual reality experiences. They will promote interaction with the environment through gamification and digital storytelling, and they will provide guidance to students on university life and activities like teaching, research, and third mission. Through the totems, the university community will be also able to access a chatbot that we created. Actually, it is an artificial intelligence, Romolo assistant, who will answer questions by the students, but by any user that will, you know, be part of the community at the university premises. The goal is to improve access to information, facilitate interaction between the university and the surrounding community by creating an immediate and effective channel of communication. The virtual museum that will be accessible through the totems will foresee 3D objects experiences that will be put on the virtual museum and are taken from the heritage of the area, so the heritage of the Roman area from the urban and suburban context. So, you know, the most important heritage in the world, actually. We realize the virtual museum. We will study also the perception of generative AI creations, because objects will be reproductions of course, 3D models of actual objects, but also objects created through AI. And we will carry out object-based learning experiences. We will also connect these objects to haptic gloves that will make the experience even more real. We will manipulate these objects with the users. The benefits are multiple. We will have interaction and learning through multi-sensory experiences, but we will also meet expectations related to inclusion and the possibility to help people with different kind of protected characteristics. In order to make the knowledge of the contents related to the project more entertaining, more involving, we found a way of starting from a plot device that is based on a graphic novel. The graphic novel runs around a group of researchers, and here you can see the main character with Theo, and he is a telecommunication engineer who coordinates a group of researchers that are inspired by some of the best researchers in our university. Anyway, those that are listed in the 2% Stanford list of best researchers in the world, and they work in a newsroom where they try to solve different mysteries and crimes, and through this device we tell stories about the project, about the Restart project, and about research, trying to involve young people in research, in studying, in accessing university contents. Gamification will be implemented, and so we will have not only the virtual museum where students will be involved, but also we will produce a video game related to the adventures of the group coordinated by Theo, our telecommunication engineer. We have also started an artistic setup of the totems according to many studies that underline that the presence of art installations in social and public spaces proves particularly effective in promoting community involvement in cultural initiatives, and so social inclusion and quality of life of citizens. But the most important thing that I wanted to communicate to you today is that we have already 413 students from secondary schools of the area in Rome registered to take part in our program of activities that are not only related to the possibility to access the virtual museums and other contents, but they will work with us in specific pathways for transversal skills and orientation. This is a dual learning program where students from secondary school, these 413 students from secondary school are involved, and they will work both online and on-site, having these kind of experiences at the totem connected to the 5G antenna. We put at their disposal a platform, an e-learning platform, where they have a series of activities to carry out. First of all, in the first part, they have an introduction to the Restart Grand Challenges, and they have some tests related to the understanding of the grand challenges. Then they have a session devoted on how to create a virtual museum. So they will learn how to create a virtual museum, how to create a virtual environment where to put also 3D objects. So they will also learn how to model 3D objects. Then they have another area where they learn how to draft a graphic novel that could help the communication of certain contents, and also how they could communicate scientific concepts through a graphic novel, which can be very, very involving, and also could be the start, and they will learn also how to create a video game. The graphic novel is entitled Restart to the Future. These are the 5 main characters. Again, they are inspired, as I was saying, to different areas in science and in research carried out in our university at top level. And the graphic novel is accessible through the totems, but if you're interested, I will be very glad to share it with you. And the most recent advancement is that the 5 characters of the graphic novel will be our guides in the museum experience. We will have 5 3D avatars that will guide the users through the virtual museum room. Here you have some publications related to the activity we carried out so far. Again, some references, and I think for now it's all, and I'm at your disposal if you need other explanations or you want to read and access our tools. Thank you.
Thank you, Antonella. I think we have room for one quick question from the floor. Okay, if there isn't any, maybe I have one. Thank you, first of all, for this engaging perspective, which is quite different to the one we are used to. But apart from that, do you have any plans to maybe extend your work to other subject categories which are not, that are not exclusively, say, teenagers, or as opposed to them?
Absolutely. The idea is to involve different categories. Of course, we thought that the first target groups could be the students from secondary school, especially because our main goal was to let young people understand and know what is a project in telecommunication and why telecommunications are so important, and also to start motivation in, finding the role of research in their everyday lives. And also the other goal was to have the opportunity to be with these young people for some time in order to let them think of enrolling telecommunication courses at university. So that was our main.
Thank you, much appreciated.
Yeah, I know. And also, yes, but for us it is very important to involve the whole community in the area. So the idea is to have the possibility to involve also elderly people and other communities that need to develop especially technological skills, which are vital to be active citizens. So, from 0 to 99, as we always say, we will involve different kind of targets, and especially marginalized people that for any reason are out of the game.
Okay, so let us thank Antonella once more, and let's move forward back to reality with Marco Rappelli and his talk. Marco is from Politecnico of Torino. Please, Marco. Rappelli.
Yes, Rappelli. Okay, thank you. So, good afternoon, everyone. I'm Marco Rappelli, and today I would like to talk to you regarding our work on maneuver coordination using vehicle-to-infrastructure to improve traffic efficiency at intersections. This work was held by Alessandro Bazzi and Lorenzo Farina from University of Bologna and WeLab, me and Claudio Casetti from Politecnico di Torino, and Barbara Masini from the National Research Center of Bologna. The motivations behind this work are the increase of traffic congestion and emissions in big urban areas, which which lead many studies to focus on signal-free intersection, where vehicles can employ some kind of maneuver coordination in order to pass the intersections without stop and goes. Indeed, the stop and goes are known to increase both traffic congestions and emissions. There are actually several works in literature focusing on signal-free intersection with maneuver coordination, but we actually observed that they either concentrate on the communication protocol or on the control algorithm, while instead in this work we both design and validate a so-called first-in, first-scheduled algorithm in order to schedule the priorities of the vehicles at the intersection, and we also focused on a related communication protocol. We design our model with a four-way intersection with a control zone around the intersection and a conflict zone divided in subzones where the collisions may occur. We assume to have full cellular coverage around the intersection, basically inside the control zone, and we also assume the presence of a multi-access edge computing server hosting our intersection controller. Our algorithm starts as soon as the ego vehicle enters inside the control zone. Since the trajectory of the vehicle is assumed to be known a priori, the ego vehicle can coordinate with the intersection controller and compute the time it will reach the conflict zone. In order to do this, the position, the speed, and the acceleration profiles are calculated by the ego vehicle without the need of coordinating with other vehicles present in the intersections. Indeed, the ego vehicle will only coordinate with the intersection controller. For this reason, also, when the profiles are defined between the ego vehicle and the intersection controller, the profiles will not be modified anymore. For this reason, vehicles are served in the order of arrival, but maybe exit the intersection in a different order. And this is the reason why we called our algorithm first in, first scheduled. There are only a few constraints on the motion pattern of the ego vehicle. In particular, the initial position and the final position has to be fixed to the beginning of the control zone and the beginning of the conflict zone, respectively. The speed is also limited to a maximum speed or a lower maximum turning speed in case of turning inside the conflict zone. And also the acceleration is limited between a minimum and a maximum value. Note that the profile setting needs a trade-off between efficiency and time, but the profile optimization here is not the main focus of this work, which is instead the scheduling of the priorities of the vehicles at the intersection. Our first-in, first-scheduled algorithm is a prescriptive solution, which basically works in 3 steps. So on the first step, we have the ego vehicle, which calculates the time it will reach the intersection, assuming that there are no other vehicles present in the scenario. And it will calculate the time it will reach the intersection and send it as a proposal to the intersection controller. On the second step, we have the intersection controller receiving the proposal of the ego vehicle, and it will check if there are any possible collision with other already scheduled vehicles before the intersection, inside the intersection, and also after the intersection. If any possible collision is found, then the time at the intersection of the proposing vehicle will be delayed. And the resulting time is then prescripted to the ego vehicle. Not that for this behavior, we may have the ego vehicle which may exit the intersection also before some other vehicles which are already scheduled. Eventually, in the last step of this algorithm, the ego vehicle receives the prescription from the intersection controller and recalculates its motion profile accordingly. If the ego vehicle agree with the proposal of the intersection controller, then everything goes right. Otherwise, the procedure is repeated until an agreement is found between the ego vehicle and the intersection controller. We also envision to have a backup mode in case the speed of the ego vehicle goes below a minimum, or if the procedure cannot be completed in time. We use Sumo Simulator with Python script in order to model our first-in, first-scheduled algorithm. And we generated uniformly over the four road segment our vehicles with the same turning probability thanks to a classic Poisson process. We modeled the transmission between the ego vehicle and the intersection controller by adding a random delay between 20 and 100 milliseconds. And eventually, we compared our solution with a few benchmarks. In particular, we compared it with a classical priority-based intersection, a traffic light-based intersection, and a classic first-in, first-out intersection with ideal communication. And we focus on, for our metrics, travel times and emissions. In this brief video, you can see our scenario, where there is the intersection and the control zone depicted with the red circle. You can see the vehicle moving there, and you can see that the vehicle colored in white are the one which are normally operating, which means they are or before the intersection, or they just passed the intersection. The vehicle colored in green are the one with the profiles already defined with the intersection controller. If you focus on the entrance of the control zone, for example, in the blue rectangle highlighted there, you will see that the color of the vehicle change in red for a few milliseconds. This is the time in which our algorithm is working and in which the proposal and the prescription are agreed between the ego vehicle and the intersection controller. As you can see, it's very few time, which means that our algorithm is actually very fast. Moving to results, we have here the results regarding the travel time for both a, let's say, low density scenario on the left and a higher density scenario on the right. You will see that our scenario is the one with the green line, which basically outperforms all the other benchmark we focused on. And same here for the emissions, with, again, on the left, a low density scenario, on the right, a higher density scenario. Moving to conclusions, okay, basically we present our first-in, first-scheduled algorithm, which with a related communication protocol, which advanced both in terms of travel times and emission the literature. As next step, we would like to apply this on different type of intersections and multiple intersections, also with more realistic cases, as for example the one you see here in this brief video, with 4 different intersections inside a district in Verona. We also would like to include some variety in our scenario, for example, adding also human-driven vehicles, or also non-connected vehicles and vulnerable road users. We would also like to inspect a more distributed scenario with vehicle-to-vehicle communication and not just vehicle-to-infrastructure. And eventually, we also would like to improve our field test campaign. Thank you for your attention. If you have any questions, I'm here to answer.
Thank you. Thank you, Marco. Perfect timing. Okay. Any question? Okay. Antonio?
There are cars entering into the control zone that are traveling in the same direction of the controlled vehicles, right? So while you receive the schedule and the prescription on the speed, you may reduce or increase the distance with the other vehicles. This can become a constraint because, for example, you cannot go too close the other vehicles? More in general, there are other conditions that should be considered in the way in which constraints that you need to be considered for scheduling the vehicles in the intersection.
Well, okay, let's say that during the exchange between the ego vehicle and the intersection controller, which is of course is the most critical part, we assume to have vehicles with a constant speed. By the way, as you saw, is also very few milliseconds, so actually it's an assumption, but it's also quite realistic in few milliseconds. Yes, instead, in the control zone, you are basically, when you already have an agreed prescription, then both the speed profiles and the acceleration profiles as well are already determined, and the vehicle...
Independently per vehicle, or?
Independently per vehicle, yes.
So you may have not under control the distance between two vehicles, right?
It's let's say, the intersection controller knows all the motions of all the vehicles, and so for sure will be not, so it's like a centralized control, so the vehicles per se do not know which are the agreed motion profiles of the others.
No, yes, the point is that the controller can add any constraint on the...
Yes, exactly. It's all controlled by the controller, so it's all centralized in this case.
I see, okay, thank you.
Okay, maybe I have another quick question for you, Marco. What type of model did you employ, did you rely upon for evaluating the emissions?
Well, okay. Actually, this is a question maybe the guys from Bologna
We'll take it.
Yes, know better than me. But I think it's the classical one of Sumo. I know that Sumo has some emission kind of models, and so is the classical one of Sumo.
Okay, thank you again, Marco. And let's thank the speaker. And let's move forward. Now we have Tiziana Cattai from the University of Rome La Sapienza. Your turn, Tiziana. Thank you.
Okay, so good afternoon, everybody, and thank you for who is still here. I am Tiziana Cattai, and I am currently working at La Sapienza inside the Watering IoT Focus project that is coordinated by Francesca Cuomo. And in the following, I will present our current work on the characterization of water distribution networks through higher order interactions. Before turning into the proposed methods, I would like to briefly present the general context in which what our problem is. And specifically, in this slide, we can see the key factors that mostly affect the management of water distribution networks nowadays. Specifically, one is, of course, the population growth. Then we have the climate change that generates unpredictable precipitation patterns together with complete drought periods. The status of water distribution infrastructures that are aged and poorly maintained. Then we have disparities in the water access, especially between urban and rural areas. And the lack of smart, that means advanced, cost-effective, and energy-efficient solutions in monitoring water distribution networks. So inside this context, the Watering IoT project aims to propose analytical solutions and simulative approaches to analyze IoT data coming from sensors measuring water activities that are sensors coming from the telecommunication networks and also sensors at the application level, with the final aim to develop new possible solutions for different problems, such as the sizing of the network, so the design of the network, leakage detection, and user profiling, for instance. Here on the left of this slide, we can see one of the most classical approach to deal with water distribution network that is based on graph representation. Specifically, water distribution network kind of naturally fit into a graph where junction can be modeled as nodes of a graph, while pipes can be represented as links. And in this structure that is represented on the left, we can define signals on this graph that can be node or flow signals. And we can define all the classical quantities that relate to graph, such as the adjacency matrix and the Laplacian matrix. But then what is the limitation of graph? The limitation of graph is that they only take into consideration pairwise connections between graph nodes. So our idea was to go beyond graph, trying to incorporate multi-way relational descriptors with higher topological representations through what is called topological signal processing. So our idea is to come to another space that is the space of cell complex representation. In general, we can define cell complex of order K, a generic order K, but we stopped at order 2. So a cell complex of order 2 is defined as a set of nodes, edges, and polygons, as we can see in the plot on the right. The polygons are colored in the figure. So in this new space, we can define cell complex of order 2 and all the quantities that characterize this cell complex that are the graph Laplacian, for instance, but we have several graph Laplacians. The L0, as it is represented there, is exactly the graph what corresponds to the graph Laplacian, what we already know. But then we have an upper Laplacian, that is what we call L1, that is made by two principal contributions. One key aspect is that this Laplacian L1 has a number of rows that is the number of edges, and the same for the columns. So it's a matrix that is n edges per n edges. So the idea is that the two contributions of L1, so these new Laplacians, measures how the edges interact in two ways. The first part of the graph Laplacian measures how edges interact through nodes, while the second part measures how edges interact through polygons. So this is a more complex Laplacian that takes together into consideration this complex structure. So the advantage of using this complex structure is that we can consider more than pairwise connections, but all the complex relationship that happens in complex domain and interacting domains. One of the big efforts that we did in this context was to transform all the physical laws related to water distribution networks inside this new space and related to cell complexes. Specifically, we use all the mathematical properties in this new space in order to transform what are the mass conservation laws, etc., in this new space. And we obtain this nonlinear system that takes everything into consideration, all the relationship, but also this modeling in this complex space. So the idea is that through this nonlinear system, we can find pressure or flows from a subset of them that we can measure. So the main idea of this work is that, okay, we have this complex model of water distribution network, and then we can decide that we sample signal values that can be pressure values or flow values, for instance, and we can reconstruct them through this kind of this nonlinear system. So the general idea is represented here in this slide. So we have on the left the water distribution network that is made by junctions, pipe, and also active elements such as pumps, valves, etc. Then we can derive our model and obtaining a topological based representation. And then we can decide that, okay, we can decide to measure the flow on some pipes in the network and reconstructing all the other values that we do not sample. In order to test our method, we consider realistic data obtained through APANET software that given a real topology generates realistic flow values and pressure values. And we also did another big effort in order to consider also this presence of active elements that are usually neglected in the state of the art. So then we obtain our topological representation, as we can see on the right. And we formulated an optimization problem with the aim to reconstruct, in this case, flow values. So this is our optimization problem, our minimization problem, constituted by in which the objective function is made by two different terms. The one circled in blue only takes into consideration the sampling and reconstruction, neglecting all the physical properties of water distribution networks, while the second part, circled in orange, and ensures the compliance with the physical laws that happen in those kind of networks. If we see the first term of the optimization problem, the one in blue, we can see that we have the U matrix, that of course is the eigenvector matrix, but the question now is the eigenvectors of what? So we can decide to compute this eigenvector matrix from one graph-based representation, neglecting all the cell complex and everything that we have said, or the cell-based representation. So in purple, we have our proposed approach, in the sense that we can compute the eigenvectors of the Laplacian L1, that is the big Laplacian made by the two terms that I have explained before. And our idea is that this kind of representation, this kind of Laplacian, and then the eigenvectors related to this complex Laplacian can help the reconstruction. One thing that I have to mention is that in order to obtain the optimal sensor locations, we used in this case one sampling method coming from the state of the art that was already defined for graph signal processing, so for signal processing graphs, but we readapted it for cell complexes. And here we can see some results on the reconstruction performance. So how can we reconstruct the flow values if we only measure a subset of them? And you can see in particular the mean square error between the estimated and the real flow values, varying the number of samples that we measure. And we can see in purple the curve related to the L1, so the complex the complex Laplacian that takes into consideration also the cell complex, that is lower, quite half, almost half of the other. That means that using cell complex representation help the reconstruction. Here is just an example of another network in order to assess the ability of our method to generalize in different topology. And here I just wanted to mention the case in which we reconstruct not the flow vector, but the pressure values, if we consider a subset of them, is more or less the same approach. The only difference is the problem that we obtain is non-convex, so the resolution of this kind of optimization problem is a little bit more complicated. And one thing that I forgot to mention is that we also consider the presence of water demands. That means that the different users in the different locations of the network can request water from the network. So we take also in consideration this realistic element. So to conclude, we have demonstrated the ability of topological signal processing to reconstruct the flow and pressure values in the network, giving a way to optimally monitoring water distribution networks. And in the future, we will investigate the possibility to have a dynamic model in which we also include water leakages that are a big problem in water distribution network, that has more or less the behavior represented on the right curve, because we have a recast of the water in some pipes of the network that once that starts, then remains persistent. So thank you for the attention, and if you have any question, feel free to ask.
Thank you. I think we have time for one quick question coming from the floor. Okay. Well, I have a sort of curiosity more than anything else. Did you ever think of using alternative approaches like Petri nets, for instance, as opposed to this signal processing oriented type of solution
Yes,
that you
yes, of course.
were adopting?
Yes, of
Just
course.
a curiosity.
Yes, 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 of course. I thought about this, but in one of the problem in water distribution network management is that also we do not have a lot of data.
Okay.
So usually the
Sampling.
modeling,
Okay.
yes. So the modeling approach is usually better than data-driven methods. So this is one idea. So it's simple. Once that you define the model, then it's simple to apply this method. And also computationally, once that you have the topology, it's really fast.
Okay. Okay. Thank you again. Let's thank our speaker. And last but not least, we have our last presentation by Martin Galcani. Is Martin here? Okay. I hope I pronounced your name correctly. Did my best. Okay, so the floor is yours.
Hello, good afternoon. I'm a PhD student at the University of Padua, and the topic of today is the thing that when I joined to the Signet group at the Information Engineering Department at the University of Padua, we have started work on around 2 or 3 years ago, and we worked on a platform for monitoring biodiversity conditional environment in Venice Lagoon, specifically for that. So this project is under. Okay. This project is under AquaSmart project, which has partners University of Sapienza and Catania. And the aim of the project is making a sustainable device for underwater and above water for controlling the coastal environment and also studying the climate change and biodiversity. With this definition, we are going to Venice environment, and it's one of the challenging environment for studying because, as you know, Venice Lagoon is kind of industrial environment, so industrial activities will affect on marine's life. So also the coastal area is really important for studying as the raising of the sea level, and also the other important thing is climate change, and also biofouling activities and biodiversity here is really important for studying. So it's really important for studying, but we have lots of challenges. The first challenge is extremely variable environment because the Venice Lagoon condition can be different from the cold months and hot months. So like the winter, it will be completely different from the summer. Biofouling activities again, and also the sea level, tides, and the other things. And also, difficult to sample in many situations because we don't have access to lots of points in Venice Lagoon. And this is the other problem that we couldn't manage at the beginning. So, in collaboration with the Department of Biology and our department, the Information Engineering Department, we found a solution which is cost-effective and real-time, and we called the device that we made SandSwitch because of the shape and the other things that we will see in further. And this device made for addressing these issues that I mentioned, and this is just the first phase for going to that device. So the main features of SandSwitch is being cost-effective, because we use some kind of sensors that they are cheaper than the others, similar conditions with the good accuracy. The second thing is real-time operation. It samples each 10 minutes the quality, the parameters of water, and you can see the results in your network, like at home or somewhere else. And it's energy efficient. Right now, we reached to a good result that with single time charging for lithium-ion batteries, you can reach up to like 3 or 4 months. So it's a really good result. And it's Arduino powered device. We didn't use very expensive ICs or chips and also electrical components. So it's easy to access. And also we did the data collection and visualization with AWS, Amazon Web Services, and also Grafana. So as I said, the first phase was moving from manual sampling to a device that can send the information regularly and monitor the condition of the Venice Lagoon, and specifically for that condition, like each 10 minutes or something. So the first phase was this research device that you can see here. It made by 2 wooden panels and a live buoy in the middle. Just this is a simple thing that we wanted to be sure that the device works well. Then we use this kind of cheap sensors, as you can see here, the information. And these sensors deployed, implemented, installed on the board like this. As you can see, we use pH sensors, turbidity, dissolved oxygen, electrical conductivity, and liquid level to be sure that the device is in the water and the results are reliable. And also the other thing is GPS to be sure that where is the exact location of the device. First, we started with this ugly shape in the left because we wanted just to be sure that the electrical components works and we can have a good connectivity with the sensors and Arduino. At the beginning, we used 2 Arduinos because we had kind of interference between the signals because we worked in saline environment, the salty water, so the water could work as a very light conductor, and some sensors were based on voltage, so they had interact with each other. So we had to use 2 Arduinos at the beginning, and also with lots of battery, as you can see. Then we moved to the other board with physical relays and some cheap ICs, and as you can see here, it became more in shape and also more user-friendly. So it was time to test it in the real case scenario. First, we put it in Canale Piovogo in Padua. It was close to the department. And then we went to the Chioggia with a little bit more harsh environment. As you know, there is some tides, there are some waves, and we wanted also to test the device that if it works well or not. So the result came up with these kind of results. As you can see, that for dissolved oxygen, pH, temperature, liquid level, turbidity, electrical conductivity, and also GPS we should scroll the page a little bit down. But anyway, it has a good result for being in Lagoon for a couple of weeks. But we had a very big problem, that's this one. So we tested this device in summer, as you know. In summer, Venice Lagoon condition is not really friendly. We had lots of biofouling activities that ruined the device completely after 1 month. So what we had to do, we moved to the second phase. We changed the product to the plastic prototype. And it has 2 plastic boxes, which there is an electrical component inside the right one. And we moved it in Piovogo, and we left it for a couple of weeks to be sure that it's sustainable and we can reach to a good results. So with the help of one of the last spin-off of our department at the Università of Padua, we could move from the previous research staffs to a new PCB integrated board, as you can see here. So it's more professional, more integrated, and also more user-friendly. It's just like plug and play. You just need to install your sensors on the pins and then plug your battery and use your device. This is the sensor placement in the new sandwich. As you can see here, we have all the sensors that we had previous, but in a better shape, in a good, and in a row, in a good way. And as you can see in the right hand, we see some copper around some sensors because we wanted also to check the biofouling activities when there is a copper around the cap of the sensors. So it was also, again, time to check these prototypes. First, we moved to Canale Piovago. As I mentioned before, we left it a couple of weeks. The results were satisfying, but still, as I will show later, we still had some biofouling activities. And the right one is related to tested again in Chioggia. But in Chioggia, you know, we have some like harsh waves that comes up to 1 meter, so we still are thinking about to make it really good waterproof. This is the result in Canale Piovago after about 2 weeks and also after 1 month. So you can see that there are a lot of biofouling activities, and you know, Piovago condition is not like lagoon. It's a bit smoother. It's not very, it doesn't have very biofouling activities, but still we have lots of biofouling around the sensors. So we are thinking about the other solutions, as you can see here, the copper or the other like sprays or something, anti-fouling solutions, but it's in the second phase and the third phase that we are still working on, and we need to discuss with biological people. So as a conclusion, I want to say that the first phase actually helped a lot because we could solve the problem of manual sampling. So it was like, previously it was like 1 time in a day that they went to the sea and they wanted to sample every morning and then publish the results and so on. Right now, they can have the result each 10 minutes. So it's a really good step. The second thing is it's a low-cost floating sensor device. So you can have this kind of device like 1/5 or 1/3 time of the expensive monitoring devices. The third thing is biofouling that we are still thinking about because there is no way to escape because the plant will grow around the sensors, and at the end we can just slow down the growth rate, but still we have this problem. And make a device completely waterproof, as I said, because we are working in a really harsh environment, and we need to think how it can survive in different kind of tides, and also different kind of different height of the waves, because it can also break completely the device when there are some tides in the nights. So it's really important to study more about this problem. But as I said, we are in a really good phase. So the Subsea Pulse decided to receive some orders from pre-ordering and solve the other problems, and also have collaboration with the other researchers and users. So we are still available to have some pre-orders for deploying this device to the other water condition, not just for lagoon. You can use it for the rivers. You can use the other coastal areas. And this is the next step for other potential customers. And with that conclusion, I want to finish my presentation, and thanks for your attention.
Thank you, Martin. Time for one quick question from the floor. None? Okay, maybe actually you already mentioned the potential adoption of some coating to protect your case, and I believe there is room for that, as well as for maybe moving to a case with a higher protection in terms of waterproof properties like IPX7 or whatever.
we are thinking about a solution that also be environment friendly.
Okay.
And also can survive in a really good condition, like high waves. And I know that the other kind of plastics, even if we use some covers around it, the boxes can be worked, but also we should know that around the covers can biofouling growth. So we still have problem, like we should clean each couple of weeks, couple of months, and we are still thinking to how to make it longer and longer. Like, for example, controlling the condition each couple of months, not couple of weeks. The other thing is the batteries should be replaced. So we cannot make a very fixed device that just leave it for last couple of years. And the battery should be replaced each couple of months. And then we should make a portable device that the other users can easily open it, change the batteries, clean the sensors, calibrate it, and then use again. So we are still working in the solutions that be still cost effective, and not because there are still lots of expensive solutions that we don't want to go to that way.
Okay.
So being cost effective and also a good condition for the environment and for the users.
Okay, I understand.
Thank you.
Thank you, Martin. Okay, let's thank again our last speaker. So and this concludes the very last session of today. Let me personally thank Ilenia, and also from all of us. I think we owe you a lot for this great organization in Palermo. We cannot compete with you in Northern Italy, I'd say.
Thank you. Actually, I want again also to thank Ilenia and all the people here in Palermo for the extraordinary organization quality and really, I mean, I think it was really a successful workshop. I hope that you all enjoyed not only Palermo and the catering that Ilenia organized, but also the technical content of our workshop. I think that we should also try to build on what we have seen in these 2 days for the final part of our project. So we will organize, as I mentioned at the beginning, yesterday, 2 more plenary workshops for the presentation of the final results of Restart, and we will focus on the presentation of demos and proof of concepts. This will be our main target. We will also need to try to be effective in the presentation, try to find the best way for either show some of the results in videos or have live demos presented in these kind of events, because of course this is part of the impact and interest that we can create in the community, in the large community that is looking at us as the most important research project in Italy on telecommunications. So we need to work hard in this last year. I will contact you and Nicola as well for requesting contributions and also help us during the last year in trying to be at your service in trying to present the results that you produce at best. I just want to remind the first of these events, which will be in April 8 and 9 in Rome. That will be an event important also for the young researchers and PhD students that we recruited. So again, Nicola mentioned me that unfortunately Nicola had to left for a problem. Nicola reminded me that it's important for you to ask to everybody that is part of this community, in particular those that have been recruited by Restart, to register for the event, if possible, by today or this weekend, because then this Monday they have to confirm the location of the event in Rome. That event will be important not only for trying to show the opportunities for the young researchers to what can be done after Restart, but also for we will have a number of people attending, political stakeholders and decision makers, and as we mentioned several times, the impact of what we do is also made of political decisions that can shape the economic situation of the sector we work in, and presenting our results in that kind of venues is important. The next plenary will be in Naples. Well, probably. We still need to have the final confirmations, probably on June the 30th and July the 1st. We will send you confirmations as soon as we have all things set. The final step is the announcement of the winners for the best posters. So if I can have the slides. Okay, yes, thank you. As usual, we give an award to the best 3 posters. So I will now list the short-listed 3 posters. Let me see if it works. The first one is Integrating Digital Twin Federation and Intent-Based Networking for Optimized Performance in Ethical Next-Generation Networks. I invite the authors, if they are still here, to come, please. Good. Congratulations. Now we'll see the exact final list. The second one is security monitoring for 5G private networks, a platform for traffic analysis in 5G as a service scenarios. The last one is a usual suspect, towards communication network virtualization, asset administration, shell, and AI-powered cloud-to-edge integration for realizing a digital twin of a coherent network. Next time, a short title, please. The others can come, please. Marco, it's always you, right? Good. We don't have the printed certificates, but at least we will send to you, of course. So let's see the final order and see. So runner-up, the winner is Towards Communication Network Virtualization. So congratulations. Come here. Come here. Congratulations. Sì, sì, vai. Foto. No, vai tutti quanti. Great. And then, of course, the others are runners-up. Thank you very much. Congratulations. So, thank you all. And I'll see you in Rome and then hopefully in Naples. Thank you very much.